Okay, so let me actually start over. We have this example problem where we have an ideal pulley, an ideal rope, two masses connected by the ideal pulley rope. We have a spring with stiffness K. The values of the masses and the stiffness are given. We are told that the velocity of the mass M1 is upward 0.1 meters per second, with the implicit assumption that velocity of mass M2 is downward, same magnitude, assuming that this rope remains taut. In other words, it doesn't go slack, nor does it change length. Um, and then G is 10 meters per second square. I may give G equals 10 meters per second square for some numerical problems, just to ease your calculation, if you want to do it by hand. Okay, so, and then you're also told that the initial stretch of the spring relative to unstretched is 0.05 meters, okay? The spring initially at time t equal to 0 is already stretched. In other words, it's transmitting some force. That's the initial stretch, okay? When S equals 0 is when the spring is called unstretched and doesn't transmit force. In this case, it already transmits force and already has some energy. That's what we mean by this statement. And then you let go of the system with these initial sort of conditions, and you're asked to determine the maximum stretch of the spring, and we are going to call this maximum stretch S sub F, or S max. In all these problems, when there's a spring and the spring goes to its maximum stretch, usually the things attached to the spring momentarily come to rest. That's sort of what we mean by maximum, because beyond that, if it didn't come to a rest at that point, it would sort of continue to stretch and it would no longer be the maximum, is the idea. Rohan asks, for problems on the midterm, do you want us to solve problems symbolically or should we plug in numbers? I would say whatever you like, but if we give you numbers, yes, so for all problems, we'll give you numbers, unless it's like well, typically for most problems, we'll give you numbers. And we do expect you to give us numbers for the final answer. But whether you do everything symbolically and then plug in the final step or carry numbers along, that's really up to you. So either is fine. Yeah. Okay. Cool. So that's the problem. I was just saying, when the spring is maximally stretched, everything comes to rest. Because if it didn't come to rest, then it would continue to stretch and it would not be the maximum stretch any longer. So when we say maximum, things come to rest, at least locally, okay? Okay, so this is a work energy problem. This is the work energy balance equation, P initial plus K initial plus work done by other forces equals P final plus K final. And I like this version, as I mentioned last time, where we go change in potential energy plus change in kinetic energy equals work done by other forces, where by other we mean things like friction or other external forces that are not gravity or springs, basically non-conservative forces. So, okay, so we have this equation. We just need to plug in the various terms. Let's go with kinetic energy initial. We are told the velocity of the masses up and down, half mv square, half mv square. We plug in the numbers and we get this quantity, let's say. And then as we just discussed, Ke final is going to be equal to 0, because when the stretch is maximum, the masses momentarily come to rest and then sort of start returning back, basically. So Ke final at the moment of maximum stretch equals 0. And then we next have to figure out what the potential energy difference is. We have two kinds of potential energy for this problem, springs as well as gravity. For spring, we've been given the initial stretch, 0.05 meters, and we've been told the spring constant. So the spring potential energy is just half K, how much it has stretched from the stress-free state. And the final stretch, we don't know. That's what we are supposed to find. Initial stretch is given. So you just go half K S final square minus half K S initial square. And plugging in K equal to 1,000, you get some quantity. SF is unknown, but this quantity is numerical. So here is a picture, basically, of the situation, I suppose. You can imagine the unstretched case of the spring, and then initially at time t equal to 0, the spring is already stretched, and that stretch is what we are calling S sub I, which is 0.05 meters. And then finally, at the moment of maximum stretch, that's S sub F, okay? So this point moves from here to here, I suppose. Okay, the spring stretch goes from SI to SF. That's kind of the mental picture that you want to have. Okay, so anyway, so for spring, this is the thing. A common mistake that I see for spring potential energy difference is sometimes people write SF minus SI whole square, like half K SF minus SI whole square. That is not a correct formula or correct expression for the spring potential energy difference. So it is SF squared minus SI squared. Very important. They're not going to be equal to each other in general. If both are non-zero, then they're not going to be equal to each other. SF squared minus SI squared is not the same as SF minus SI whole square. But the correct answer is initial potential energy, which is half Ks square, final potential energy, which is a different half Ks square, and you want to subtract the two things. Okay. Sometimes we might ask things like work done by the spring. If you want to know that, you just find this quantity, and the negative of that is the work done by the spring. Okay. Negative of this difference is basically work done by the spring. But here we just care about potential energy. Same for gravity. So because basically this point goes from initial here to final here, well, let's look at this picture. If this point goes from somewhere to somewhere else, this mass moves up by the same distance, and this mass moves down by the same distance, by which the spring has increased its stretch. Okay, so the movement of the masses, so mass 1 goes up by SF minus SI. So its potential energy difference is M1G SF minus SI. This is going to be a positive number because the mass rose. In other words, its height increased. For M2, the mass M2, it's actually going to be a negative because this mass falls down. Like if you do Y2 final minus Y2 initial, then this is going to be the expression. M2G with the negative sign of how much the mass 1 went up. Okay. So this is capturing the fact that mass 2 loses potential energy, this gains potential energy. Plug everything given, you get some expression. You get SF, as still as an unknown here in the potential energy expression as well. And then the last piece in your potential energy expression or in the work energy expression equation is work done by other forces, which in this case is just 0 because this problem so far only has springs and gravity. And we've already discussed that things like inextensible ropes or pulleys do not do any work. So we only have springs and gravity. So those are conservative. Those have already been taken into account in potential energy. So I suppose this is equal to 0. Okay, so now we are going to just put everything together. P final minus P initial, K final minus K initial, work done by other forces. We put in the spring potential energy difference, gravity potential energy difference, KE difference equal to 0. And we have this equation, which is a equation in one variable, S sub F, namely the final stretch of the spring. This is a quadratic equation, which you can solve, I suppose. You're welcome to use a calculator or use the standard formula, minus b plus minus square root of b squared minus 4ac by 2a, I guess. Emily asks, what is the work done by the spring? If we were asked, yes. So we computed the potential energy change in the spring. Recall that potential energy is kind of like a proxy for work done, but it's not an exact proxy. It's sort of a negative, or it's precisely a negative. So if you say how much did the potential energy increase, it's this quantity that we have outlined. And then if we say what is the work done by the spring, it's going to be the negative of this quantity. It's going to be basically work done by the spring is P initial minus P final. That's the definition of work done by the spring. Okay. Cool. And similarly for work done by gravity. For any sort of force where you have a potential energy difference, the potential energy initial minus potential energy final is what the work done by that force is. Yeah, cool. Thanks for the question. Okay, so that's all I wanted to do for this example problem. I'll let you guys solve the quadratic equation on your own, I suppose. Any further questions? Okay. So the next thing I'm just